Computers operate in binary, ones and zeros, but binary comes in a ton of forms. First of all, you can represent binary in circuitry with high and low voltage levels. You might have 5 volts be a 1 and 0 volts be a 0. And for serial communication, it might be the opposite, or even something else. You might be familiar with Boolean logic from computer programming languages, where you have true and false. Those can also represent 1 and 0. And if you're using physical switches, you might consider on and off to be 1s and 0s. Perhaps a 1 if the switch is closed and conducting, and a 0 if the switch is open and not conducting. But the principles are all the same. You have certain operations. If you have 1 or 2 or even more inputs, you can do something, a computation to those inputs to get an output. And this is the basis of computer processing. This is how CPUs work. They have a whole bunch of fancy transistors in there, nanometers big, which I suppose is actually not big. But these transistors are chained and cascaded in fancy ways to make it work. But we can create simple operations called logic gates with big transistors, as well as MOSFETs. MOSFETs actually make it a little easier, but we can do it with our good old BJTs just fine. So first I'll show you what the operations are and the circuit diagrams that will create them, and then we'll actually create circuits, and I'll show you with LEDs. So first of all, in order to define what an operation is, we use something called a truth table. It's basically just a list of the inputs and what outputs result from those inputs. For example, one operation is called NOT. It's an inversion. So if we have our truth table, let's say we have input 1, and there's only 1, and then we have output. Now, the input can be 1 or 0, true or false, on or off, high or low, however you want to look at it. I'll use 1 and 0. Input can be 1, input can be 0. Either one. So only one input, only 2 options, there you go. If the input is 1, the output is 0. If the input is 0, the output is 1. It's the opposite. So basically, the input could be 1 if a car is blue and 0 if a car is not blue. And your question is the car not blue? Is the car something other than blue? Well, if the car is blue, it's not something else. If the car is not blue, it is something else. That's how a truth table works. It converts the inputs to outputs. So let's just get that out of our way a little bit. Now let's say we have our input. We have I1 here. This is a voltage. It's referenced to the ground, the 0, the reference voltage. And let's assume that it's already current controlled. If this is a direct connection to power through a switch, you would have a resistor. If this is out of a transistor, you'd have a resistor through the transistor. Basically, we assume the input is well behaved. If it's not, add a resistor. All we're trying to say is there's no short circuit. Like I said, just if there is, add a resistor, because we mostly care about the voltage here. So over here we have our output. We're going to be using NPN transistors for all of this because they're easier. You can do some with PNP, but the current goes backwards and yada yada. NPNs are just plain easier because you have your control current that gets dumped and then the fresh current goes out. So with one transistor, you're generally going to have 1 transistor per input, no matter what the operation is. So let's say here we have our positive. We'll have a resistor through the transistor out to negative. So let's connect all this up. So right here we just have a simple load through the transistor. It's basically a low side switch. So the input, which again we say is well behaved, so we just don't worry about the current, we assume it's fine, goes into the transistor. And the output is here. And that's your inverter, your NOT gate. So if this is high, then that means the transistor base to emitter junction is forward biased. High on the base, low on the emitter, so it's conducting. So then we have a loop here. We have your power through a resistor, through the transistor, and out. So here is 0 volts. The transistor has a small drop through it, maybe 0.2 volts or even less. So right here we'll say is about 0.2 volts. And then up here is 5 volts, so the resistor is taking the rest. But we're sampling between the resistor and the transistor, so here, again, it's like 0.2 volts, so it's low. So we got a low as out. High in, low out. If this is low, then the transistor is not forward biased. The base to emitter junction is not forward biased, which means it's not conducting. So what we have, now when you're analyzing using Kirchhoff's voltage law and you have a transistor, if the transistor is not conducting, it's an open switch. You basically treat this exactly as if it's an open or closed switch with a voltage drop. So if this is not conducting, if this is not forward biased, it's not conducting, then it doesn't exist. You cannot draw a loop through it, so we stop. But we can draw this loop. we have positive, resistor, into the output. Now, remember that the electric field establishes the voltage, and then from there, the resistor takes its voltage drop. The resistor is not a voltage drop on its own, like a transistor is. Ohmic devices are always proportional to whatever the rest of the circuit is doing. So let's say we had a transistor here, you would have the base to emitter junction dropping a small bit, probably connected directly to ground, and then you'd be sampling there, or whatever. But the point is, when the electric field establishes itself, the resistor doesn't have a drop yet. The electric field goes through, and this is effectively connected straight to the power. And then whatever that means for the circuit, the electric field finishes establishing itself, and then the resistance starts deciding what the current is, it gets its voltage drop. But for the purposes of logic, it's directly connected to power. So when this is low, this is not conducting, and we have that. So high here, low here, high here, matches our truth table. So that is a NOT gate. So let's have a slightly different truth table. The input, then the output. Input can be 1 or 0. The output is 1 and 0. No change. This is not strictly a logic gate. There's no logic here. Nothing's happening. It's a no operation. But this is something called a buffer, which is a useful concept. It's basically used in an anti-backflow way to make sure that a later part of the circuit and an earlier part of the circuit don't interact voltage-wise. We'll get into this topic later when we actually have to use it. Right now, I just wanted to point out it exists and show it in truth table form. So that's it for the one input operations. Now, for two input operations, I1, I2, and output. Well, I1 can be 1 or 0. If I1 is 1, I2 can be 1 or 0. If I1 is 0, I2 can be 1 or 0. So there's 4 possibilities. So what about this operation? Let's say if both of these are 1, the output is 1. If this one is 1 and this one is 0, we'll say 1, 1, 0. So basically, if this one or both are 1, it's 1. If neither are 1, it's 0. This is called OR. And grammatically, it's called Inclusiveor. So what about this circuit? We have input 1 and input 2, and then our output. And now, of course, we'll use 2 transistors because we have 2 inputs. And once again, we assume these are well behaved. If they're not well behaved, add resistors. So down here, we have negative power and a resistor, 2 transistors, one over here, and both of them are connected to the positive. The inputs go into the transistors, just like before. Power through the transistors. Output joined through a resistor afterward, so effectively high side switches with NPNs now. And the output actually comes out of here, between the transistors and the resistor. So what happens if both of these are 0? The output should be 0. So let's see. So we have low here. This is connected. Again, the resistor will have a voltage drop when there's conduction, but the electric field is deciding whether or not it's going to conduct. So this is effectively connected straight to ground here, and this is connected to low here. So this is not forward biased. It's not conducting, so the resistor is doing nothing. If we go through this loop instead, we have low here, again, connected to low here, not forward biased, not conducting. So this wire is not in the circuit, this wire is not in the circuit, so there's no connection to power at all. What you have is your output connected through a resistor to ground. So this is low, and that is low. Now what if we turn one of them on? Let's turn this one on and leave this one off. So this one's high. High to low, forward biased, conducting. So now I've got power through the transistor and there. So we've got 5 volts here. Let's say 0.2 volts through the transistor, so 4.8. We got 0 volts here. So we've got 4.8 here, 0 here, and the resistor is taking the rest because it is conducting now. We're sampling between the transistor and the resistor. So we're getting 4.8 here, and the output is high. And again, if you do a loop, and you're correct, if you don't make any mistakes, Kirchhoff's voltage law, do a loop, any numbers you get from the loop, assuming you don't make mistakes, those are the numbers. So this one, of course, is still not conducting and not contributing, so this wire's not here. If we turn the other one on, this one's off, so this is high to low, conducting. So now I have power, small drop, resistor in here. So now this is 4.8 here, and it's the same thing. Now what if both are on? Well, we have our loop we already did. This is high, this is low, so it's conducting. 5 volts, 4.8, 0, so 4.8 here, but is it consistent with the other one? Well, yes, because we do that and we get 4.8 here, so 4.8 at the end of both transistors. So there's our OR gate. Now, what about exclusive OR? Exclusive OR is usually abbreviated XOR, and its truth table is as follows. Input 1, input 2, output. So input 1 can be 1, 1, 1, 0, 0, 1, 0, 0. I should really draw the lines after. So exclusive OR is the same as OR, except up here. It has to be one or the other, not both. That's the only difference. Now, I'm not going to show you a circuit for this because it's generally not useful. The way you actually do this is you take gates and other gates and combine them in a cascade fashion to create logical operations. I mean, if you're just trying to combine two inputs in a simple circuit to turn the light on or whatever, like if you want two different light switches on either side to both turn something on, then you can just use transistors and make an OR gate in your little control unit. That's one use for this, is having multiple switches, and there you go. But if you're actually making a complex digital logic operation, then you cascade the gates. And you're not going to make a device with just a bunch of transistors wired together if you have any number of them. You're going to use chips with transistors on them. So you don't want to have a billion different types of chips that you buy. Remember, we're trying to be economical. It's cheaper to buy one giant box of something and combine those, even if it takes more of them, than to buy 3 giant boxes and you'd use more of these and you got these left over and blah, blah, blah. And you have more elements in your manufacturing machine. You know, it needs more arms, it needs more time, whatever. So it's actually faster and cheaper to be wasteful sometimes. So that's one reason why you're not going to bother with an XOR gate. So let's move on to something more interesting. What if I have two different truth tables? Let's say input 1, which can be 1, 1, 0, 0. Input 2, 1, 0, 1, 0. Let's say we have output. Let's say we do 1, 0, 0, 0. Then let's say we do this. 0, 1, 1, 1. What do we have here? If neither is 1, the first output is 0. If only one of them is 1, the first output is 0. If 1 and 2, if input 1 and input 2 are both 1, it's 1. That is called AND. This is AND. And the opposite is just the reverse. It's not AND. We call it NAND. Basically, we're saying, is 1 and 2 both on? Then we don't want that. Input 1 and not input 2, not input 1 and input 2, not input 1 and not input 2. But if we have input 1 and input 2, we want not and. We just invert it. The NAND gate is the magical gate because you can take NAND gates, just NAND gates, none of the other gates, just NAND gates, and combine them to make every single other logical operation that exists. ORs, XORs, everything. And that's great. Didn't we just discuss efficiency? So you buy a giant box of NAND chips where every chip has like 8 NAND gates on it and you just cascade them and you have your entire thing. That is efficiency. On the contrary, AND cannot be made properly with BJTs, unlike the other ones we've made. You can do it with MOSFETs, but you can't do an AND gate with just BJTs because they have trickery involved. Because if you recall, and I'll show you the circuit, BJTs are actually 2 diode junctions, not 2 diodes, 2 diode junctions. And the way we have to wire them up to get the AND operation, if you use a MOSFET, it's perfectly fine. We'll get to MOSFETs in the future. But if you use a BJT, it actually activates one of those diode junctions where it shouldn't be, and you get a wrong value. So let's check it out. The way we do an AND gate is hilariously simple. We have our inputs, I1. Once again, add a resistor if you need to. We assume it's there, I2, and our out. We have 2 inputs, so we'll need 2 transistors. So let's have our positive power, transistor 1, transistor 2, our resistor. So this is basically a double high side switch, and our negative, and this is where we're going to measure. So we have, through all these together, here's our output, here's our inputs. It's basically 2 switches in series. So remember, we want a high output if 1 and 2 are both high. Otherwise, we want a low output. So if 1 is high, but we need to start at 2 because we're checking the base to emitter junction. So we start with here. So this is high, base to emitter, connected to ground, so it's forward biased and conducting. So now this ground can sneak through. It's got a forward voltage drop, so here would be 0 until we're conducting. Once we're conducting, there's a voltage drop here. But not yet. We're not conducting yet. So right now we have 0 here and about 0.2 here or whatever. So this is still pretty low. And we've got high here, so it's still forward biased. So now it leaks through again, it's conducting, and now we got the power, and now we have 5 volts to maybe 4.8 to 4.6, down to 0. Once we have forward biased these junctions, the electric field has established itself, and now it's conducting. So now the voltage here is about 4.6, which is high enough to act as a 1. Now what if we turn both of them off? This is low, low to low, not conducting, so we can already stop. This is not connected at all. This cannot contribute. So you've got ground through a resistor to output and it's low. What if this one's on, but this one's off? Now I'm about to say something wrong, and then I'll fix it. So this one's high, but this one's low. All right, so we have high to low, forward bias the junction. So it's conducting, but it's not connected to power yet, all right? Collector is, we haven't established yet. We're still working our way up. So this is conducting, but what is it conducting? The ground sneaks through. So I got about 0.2 here, but this is low. So this is not forward biased, so it's not conducting. So this is not connected to power. It's not going through. So that's empty, and you're getting low again. Except you're not. Because remember, this is 2 diode junctions. This is NPN. Base to emitter is a PN junction. A diode is a PN junction. So if this is not connected to anything, this is basically an open circuit, which it is, because this is not conducting, so this is nothing. We just have the base to emitter junction. You have a forward biased diode, and this is high, so you have current going through this junction, which if you have 5 volts might be 2 some volts or whatever, depends on all the different things you've got set up. And you're going to get something in the intermediate zone, or maybe even close enough to the high zone to count as a 1 because of the BJT transistor. If you use a MOSFET here, that won't happen, and this will work just fine because this will be 2 switches. So you can't do this. But remember how we said NAND gates can make any gate, including AND. So we don't need an AND gate. We can use a NAND gate. Let's do it. The best part is we just flip it around. We have a resistor, we measure here, and 2 transistors. So we connect these through, just like we did the AND gate, but we flipped it. We measure here. Input, input. This is the NAND gate. So we should just get the opposite. For the AND gate, if this is high and this is high, we want a high out. Otherwise, we want a low. In this case, if this is high and this is high, we want a low. Otherwise, we want a high. So let's go through it. Let's say they're both high. So this, we'll start at the bottom again, because we've got to decide base to emitter junction. So this is high. High to low, forward biased, conducting. Ground sneaks through. This is high to low, low enough. This is conducting. Ground sneaks through, but now we're connected. And then now that we're conducting, the ohmic devices kick in, and we've got 0 volts, 0.2, 0.4, or whatever. 5 up here, this takes the rest, and we're measuring between here and here. We're getting about 0.4 for these imaginary transistors. So we're measuring about 0.4 at the output, and that is going to be too low to turn even a transistor on. Transistors generally, like this, are going to want 0.7 or so. And for anything, it's low enough, so high and high, we're getting a low. Let's turn one of them off. In fact, let's turn both of them off just to start. So this one is low, so it's not conducting, low to low, not forward bias, not conducting. So this is connected to nothing. But if this is connected to nothing, then this one can't be active either. Current's got to go somewhere. Base to emitter's got to go somewhere. Collector to emitter's got to go somewhere. So it doesn't matter if this is forward biased or not, and it's not. So this one's not conducting either. Even if it wants to, somehow, it's not conducting this way. So we have power, resistor, straight to the output. There you go. So if both of them, in fact, if this one is 0 and this one is anything, this one is low, we get a high, which is the opposite. It's NAND. Let's say this one is high and this one is low. So this one is conducting, high to low. So ground sneaks through about 0.2 volts, but this is low, not conducting, and we're still connected there. So this one works just fine with BJTs because it's the base to emitter junction. The emitter lets the current out. Before, this current was able to sneak through, but it can't here because this one blocks it or this one blocks it and it can't go down. So we have a functional NAND gate. And we'll go into another video on NAND gates because as they are the universal gate, that's important enough for its own video. But there you go. Now, let's say you want an AND gate with BJTs, and you're not using a NAND gate chip, you just have some transistors, and you need an AND operation. You know, you want to launch the nuclear missile only if both people have their keys turned at the same time, so you need transistors to make sure they're both on at the same time. And, of course, you can wire that up with a switch through another switch, but let's say you want to use transistors. How do you make an AND gate? Well, we have a NAND gate that works, and we have a NOT gate that works, so we use both. We take a NAND, flip it, it's AND. And that is how you do gates. You just add them together and get different operations. So let's make some circuits. So I have here my power supply, currently set to 5 volts and 0 amps. So in my breadboard, I have some 1K resistors, 1000 ohms, an LED that's going to be our output, and 3 NPN transistors. On this breadboard, I have 2 switches with some resistors and 2 LEDs. So this is input 1, this is input 2. The LEDs will indicate which input is on, so you can easily see what we're doing and compare it to the output. So first, I will wire up my switches. So to make life easier, I'm going to put some jumpers across this breadboard, just so I can get the power through any of these rails. And then we'll connect over here to more positive, to negative here, to positive there, negative there, negative there. And then finally, I'll jumper that power across to this secondary breadboard. Now, why am I using a second breadboard? So that I don't have to rewire anything. We're starting to get into much more complicated circuits here. Many more wires, many more pieces. So keeping them separated like this is going to make our lives a lot easier. Plus I have these smaller wires. So the switches will connect either positive or negative to their middle pole. So we'll go positive to one side of the switch, negative to the other. And when you're working with this many wires, remember, if you have a failure in your final circuit, start using your multimeter and measure voltages because you're likely to have bad wires. I have had that fail many times, or sometimes they're just loose. So the second switch will also be connected to positive and negative in this way. So that's positive and that's negative. So that's connected to both sides of the switches. So then I'll take the middle pole from the first switch, I'll run it through a resistor, and I'll run it out that resistor to the positive rail on this side. That's just going to indicate input 1. So we can connect to the positive rail as input 1. I am going to connect similarly to a second resistor of the same value from that resistor over through to this red LED and out of the red LED to negative power over here. So if I turn on, let's say 20 milliamps, of course it's not conducting at all, but if I turn the switch on, we get nothing. So just like I said, get out your multimeter and start measuring your voltages. I don't consider this a waste of time. This is showing you the process. You're learning as I'm learning. So first a sanity check, measure the voltage to the positive rail, and the voltage is coming over. Measure at the start of the switch. Yeah. Measure at the output of the switch, because the switch is on, and we're getting it. So now measure over at the start of the LED, and we get nothing. How about the start of the resistor? And we get nothing. How about the start of the first resistor? And we get something. So now we decide this wire may be bad. So let's put in a different wire. Let's use this wire. And all of a sudden we have an LED. So this wire now goes in the trash bin. That's what you got to do. It's the same thing if you're trying to fix electronics. If you have a busted laptop and you want to start using a multimeter to find out where it's busted and replace a chip, well, go watch Louis Rossman's videos. He'll show you how it's done. But now let's wire up the second switch. So the middle pole of the switch to resistor, out the resistor, to the negative rail, so that'll be input 2, and then over to the second resistor, through the resistor, to the LED, the green one this time, and out. Turn on the switch, and here we go again. I did not directly buy these wires. I got them in a kit. Clearly, there was a cost-saving measure involved, and I'm going to want to actually buy higher quality wires directly. So we have a voltage there. Coming out of the switch is fine, there is fine, there is fine, there is fine, but at the start of the LED, that is fine. Aha! So in this case, it was not a bad wire, it's a loose wire. So there we go. Now we have our red LED, and we have our green LED. Now I'll put this in a different hole, try to make it a little less wiggly. And just for sanity's sake, let's measure our signals too. So the positive rail is 5 volts, negative, 5 volts. So now we have our working set of switches. So now we can just set this circuit aside, and we're done. And we can just use those inputs over here. So let's make our NOT gate. So as I said, make sure your inputs are well behaved. We've got resistors going through here, so wherever we use these inputs, we don't have to worry about it. They're well behaved. So all we need is resistors through the transistors. So the NOT gate is very simple. We have positive power into a resistor. That resistor goes into the transistor, a lot of istors. The transistor goes back to negative power. And then we have input 1 is the input to the transistor, the base junction. And then finally we want to measure our output. And we take that between the first resistor and the transistor. So here, through a separate resistor, because we don't want them competing, remember, we have different voltage drops now. Want to make sure everything is separate. Through the LED out to negative power, and it immediately comes on because both our switches are off. This is a NOT gate. If I turn the switch on, the output turns off. Turn the switch off, Oop, the output turns on. I seem to have a wiggly line here that's giving me a short circuit. So let me move that. Move it down here maybe? There we go. There we are. That's better. Wow. This is the one I directly bought, manufactured for this purpose. This is the one that came in the kit. The wires and the breadboard both came in that kit. I think I might just toss them in the trash. Bless their little hearts, but they pinched pennies anywhere they could, didn't they? So there's our NOT gate. So now we don't have to redo any of this. We can just take the input out, turn that off. Then we'll set this aside for the moment. And now I'm going to undo all this. We're going to make our OR gate instead. So for the OR gate, both transistors are directly connected, their inputs with positive power. So that's 1 and that's 2. Their outputs are similarly connected. So we have output 1 goes through to a resistor. Output 2 goes through to the same resistor on the same side. And that resistor connects to negative power. We'll just use that one. We have our input 1, if this breadboard won't suck too bad, which, oh my goodness. So input 1 is going to be the base connection of one transistor. Input 2 will be the base connection of the other transistor, which is safe because we have these going through resistors. And you can see both switches are off, assuming no wires are loose. And then the output is similarly measured before the resistor down here. So we'll put this through a separate resistor for the LED, and that resistor goes to the LED and to negative power over here. And that measures our load. So right now, either it's broken or it's working fine because neither is on. If we turn one on, good news. This is an OR gate. Either input on will turn that one on. Input 1 is on, input 2 is off, so output is on. If I turn input 2 on instead, even better news. If I turn them both on, there's our OR gate. Either input is on, that one's on. So there's how you wire it up if you have two light switches and you want either one to turn your thing on. And of course, in an actual circuit, it's going to be much easier because you're just going to use solder on a PCB and not all this crap going everywhere. So let's take our inputs out again. And now, I did mention we cannot make an AND gate, but we can make a NAND gate. So let's do that. So the NAND gate is the same as the NOT. If you notice that, the NOT gate is a resistor and a transistor, and you measure between the two. In a NAND gate, it's a resistor, then you measure, and then you have two transistors. Same circuit, just add a transistor and an input. Funny that. So we have our positive power to our resistor. The resistor going through the first transistor, we're wiring these in series now. And then, of course, if I connected this to negative power, we'd have a NOT gate. But if I connected to the second transistor, we have a NAND gate. Output of the second transistor, the emitter, over to negative power. And we're measuring from, well, let me put my inputs in first. Input 1 into the base of one transistor. Input 2 into the base of the other transistor. Then we'll wire it up. We measure between the resistor and the two transistors. So the output here goes to the LED's resistor, from there to the LED, and out. And I got to move this over because I screwed that up. Now it works. These two power rails are separate in this one for whatever reason. But right now, both inputs are off, and that is on. That's what we want, because we have a NAND gate here. For a regular AND gate, both of them must be on for the output to be on. Otherwise, the output is off. So we flip it. Instead of saying both of them are on to turn that on, both of them are on to turn that off. Otherwise, we turn that on. So if I turn one on, it's still on. If I turn the other on, still on. But if I turn both on, it turns off. And you can see how much current we have going through. I guarantee 19 milliamps is not going through these two LEDs. One thing about BJTs is they have wastage current, but it is in the milliamps, and you can add bigger resistors and it'll work just fine, so you can reduce that. I'm using 1Ks. You could easily be using 10Ks if you want, at least on the base to emitter junction inputs. But in any case, that is our NAND gate. So I have a NAND gate, but I wanted an AND gate. So what if I just hook this up through a NOT gate, right? So let's do that. Let's make a NOT gate. Let me unplug this load. So this, the output of that resistor, instead of going into my load, that's the input to my next circuit, my next gate. So let's leave that there. Let's make our NOT gate. So we have positive power to a resistor, from that resistor to a third transistor, and from that transistor over to negative power. So there's our NOT gate. Now we need our input. The output of our NAND gate goes over to the junction, the base to emitter junction, not some other junction you might have been thinking of. But then, see, our current changed. So let's measure, once again, between the resistor and the transistor. So our output to our load resistor, which is our LED, resistor to the LED, and the LED out. So now it's off. If I turn one on, still off. If I turn the other one on, still off. But if I turn both on, it turns on. That's our AND gate. It's a NAND and a NOT, because NAND is not AND. Not AND. Two negatives make a positive. And there's your AND gate. One more transistor, one more resistor, couple more wires. There you go. And you can see why I decided to have the input signaling circuit separate from the gate circuitry. I could even have had the NOT gate separate if I wanted, but there's enough space. That's why I bought this big breadboard. When you're getting into big projects, it's actually worthwhile to pick up a bunch of breadboards and have different circuits on each one. And I'll definitely be doing that and replacing this. But there we go. That is logic gates. Turn off your current. Remember to be safe. So usually you're not going to be making gates like this because you're going to be using pre-built ICs, integrated circuits, that are just a bunch of gates in a chip and you use the wires. Or you're using a microcontroller that has a CPU in it, which is transistors inside there. But like I said, there are certain switching situations, and whenever you need just a simple circuit, it's going to be much more compact when you do it on a PCB, even a prototype board. You can put all the parts real close together, and you should, because in a real circuit, when you're dealing with a real environment, the longer your wires and the further apart your parts, the more chance there is for stray electromagnetic radiation to sneak in. I believe it's called parasitic voltages, and there's also induction and other stuff. You know, they're interconnected. Basically, interference. In the US, we have the FCC, which regulates how much interference can be generated by a device, and it also regulates that a device must be able to accept a certain amount of interference. So when you're making real electronics, that's a concern. For a breadboard, it's really not. And if you're having problems, if you can, turn up your voltage. The higher the voltage, the less effect that induction will have. It will be overwhelmed by the voltage. 5 volts is actually pretty high, all things considered, especially when dealing with just a breadboard, so you're probably going to have no problems at all. Start getting down to 3.3 or much lower, some devices run on just over 1 volt, then you'll definitely have problems. But in any case, there's your gates. There's how you make logic in a computer. And you can just take those NAND gates I just showed you, and you can make a CPU on a breadboard. And eventually, I will. Just a little one. I'm not going to go crazy now. There are projects that have made breadboard CPUs that are full CPUs. You know, they're not your thread rippers, but still. But I'm going to do smaller, demonstrating ones, rather than buying, 100 breadboards and gluing them to the wall. But until then, be seeing you.